We're going to go through some example problems. In the last one, we talked about several gas laws. So we had Boyle's law, Charles' law, and Avogadro's law. And then I gave us the ideal gas law equation. The ideal gas law is actually a combination of those three laws. So we had PV equals nRT. So P was our pressure, V is our volume, N is the number of moles, T is temperature, and then R is our gas constant. So this one is also on the back of your table, your periodic table. Just make sure you use the right gas constant. There's actually two of them when you look it up. So one of them has units of joules per mole Kelvin, and then this one has units of liters atmospheres per mole Kelvin. You want the liter atmospheres one. Joules is a unit of energy, liters is a unit of volume, atmospheres is a unit of pressure. So PV, we want the atmospheres in liters one, not the energy one. So these, again, are on our table, so you don't need to memorize those. I also want to define, before we start doing problems, is standard temperature and pressure for gases. So STP. Right, S for standard, T for temperature, P for pressure. And what those are, the temperature is 273 Kelvin, which is 0 degrees Celsius. But do remember, all of our gas law problems, our temperature is going to need to be in Kelvin, not Celsius. And then our standard pressure is 1 atmosphere. So do be familiar with those. I could ask a problem that says, if we have 4 liters of gas at STP, what is my number of moles? And it kind of seems like I'm missing information in that problem, but we're not, right? We're solving for the number of moles, we're solving for N. R is constant, so we get that from our table. I gave you 4 liters, we have volume, and then pressure and temperature, because it's at STP, we would plug in 1 atmosphere for the pressure and 273 Kelvin for the temperature. So even though I'm not actually stating numbers in the problem, I kind of am when I say standard temperature and pressure. So do be familiar with those. We'll do a couple of problems, or a problem at least, that involves them here in this video. The first one though, we have a spray can. That contains 3.20 grams of propane and has a volume of 350.0 milliliters. And we want to know, what is the pressure in that can at 20.0 degrees Celsius. So this is going to be an ideal gas law problem, right? We were given volume, we're solving for pressure, we have a temperature, R is constant, and then we're given grams, but we know that it's propane, which is C3, sorry, I would give you this, you don't have to memorize the structure of propane, which is C3H8. So if we have the grams, we have moles, right? We just have to use our periodic table, figure out the molar mass, and convert. So anytime we have grams, we can convert to moles using molar mass and vice versa. What I also like to do is make a list. So PV equals nRT. I like to just, instead of taking things and plugging them right in, because often we have to do unit conversions, I'll just make my list, and then I'll do my conversions as part of this. So PV, N, R, N, T. So gas constant, we're getting that from the periodic table. And then remember that the units on my gas constant are going to dictate what my other units need to be. So my volume needs to be in liters. If I go up to my problem, it's in milliliters. So we do need to convert that. So divided by 1,000, right? There's 1,000 milliliters in a liter, 10 to the third. Or I can just move my decimal place over those 3/10 places. So I'm going to do it that way, 0.3500 liters. My temperature does need to be in Kelvin. I have 20 degrees Celsius, and remember we add 273 to get Kelvin. so 293 Kelvin. Pressure is what I'm solving for. And then my number of moles, I am giving grams, remember? 3.20 grams. It's going to be kind of small, but we'll fit it in here, of propane. And we can look at the periodic table, figure out the molar mass of propane, and then divide by that molar mass to get moles. So 3 carbons, I'm just figuring it out on my calculator here, and 8 hydrogen, I get 11 grams per mole. And because I had grams on top, I need to divide by that molar mass, right? My units need to be opposite to cancel. So 3.2 divided by that molar mass will give me the number of moles. So 0.0725 moles of propane. So now I have everything to plug into that equation. And you don't have to make a list like this. I just find that students tend to make more mistakes as far as unit conversions if they just take it right from the problem and put it right into the formula. If you make a list, then you're kind of forcing yourself to address those numbers. So pressure is my unknown, my volume, 0.3500 liters. That's equal to my number of moles, 0.0725. Multiply by my gas constant, I'm going to run out of room here, 0.082006 liters, atmospheres, moles Kelvin, I'm going to write it really teeny, and then PV equals nRT. We need to put our temperature in here, 293 Kelvin, kind of fit, and then solve for P. So just a little bit of algebra. Unit-wise, let's actually do this. And normally I'm not going to walk through the algebra with you, but right, to get P by itself, we have to divide both sides by my volume, right, because those cancel. And then 3500 liters. I just want to do this first one so we can see units canceling. So these liters are going to cancel with these liters, right? If you would have forgot to convert to liters, then you couldn't cancel them. So this is also a good check. Kelvin cancels with Kelvin, moles cancel with moles. And then the only thing that's left is atmospheres. So my units are going to come out as atmospheres when we're done. So grabbing my calculator here again. And I got that my pressure is 4.98 atmospheres. So another type of example for us. So if a gas occupies 4.00 liters at STP, what is its volume at, let's do 782 millimeters of mercury and 25 degrees Celsius? So this is a different type. We're still going to use the ideal gas law, but I'm going to have two sets of conditions, right? I have a volume at standard temperature and pressure, and then I want to know what the volume is at a new set of conditions. So what we're going to do is we're going to kind of create our own equation using the ideal gas law. The first thing I want to do, though, is write down those sets of conditions. So a gas occupies 4 liters, so I have a volume of 4 liters. And then that's at standard temperature, so that's at 273 Kelvin, and then also standard pressure, which is 1.00 atmospheres. So those all go together, right? That's the volume at that temperature and that pressure. So I'm going to put ones here. You can put I's. Sometimes people do initial and final. I'm going to do 1 and 2. Heart and butterfly, it doesn't matter. Just make sure that those all go together. And then I'm going to have a second set of conditions. I want to know what is my new volume. That's my unknown. And then that's going to be at 25 degrees Celsius. Oop, that's a 2 because they go together. And then 782 millimeters of mercury. So before we come up with the equation, our units do need to match. So if I have atmospheres on one side and millimeters of mercury on the other, they either both need to be atmospheres or they both need to be millimeters of mercury. I'm not going to actually have the gas constant in this problem, so whether it's one or the other, it doesn't matter. Our temperature, however, always needs to be Kelvin. So I am going to add 273 to this to get Kelvin. So 298 Kelvin is going to be my temperature. You don't have to memorize how many atmospheres there are in millimeters of mercury or vice versa, the conversion for that. I will give it to you. I do know that 1 atmosphere is equal to 760 millimeters of mercury. And again, I will give you that conversion factor. You don't have to memorize it. So that would be provided. So I can convert 782 millimeters of mercury to atmospheres by divided by 760. Or I can convert 1 atmosphere to millimeters of mercury by multiplying by 760. I'm going to do that one because I don't have to get my calculator, right? If 1 atmosphere is this, then this is 760 millimeters of mercury. Again, you can do it either way. If you were going to have R, the gas constant, as part of our problem, then it would have to be atmospheres because R, it has atmospheres in it and they need to cancel. I haven't shown you how we're going to get the equation yet, but I do know that my gas constant is actually not going to be part of it. So my equation, let's actually get that. So PV, this is really the only one we need, nRT. So what I'm going to do is I'm going to rearrange this. So the things that are changing, volume, temperature, and pressure, are on one side of the equation, and then the things that aren't changing are on the other side of the equation. So I already have pressure and volume on one side, so I'm actually going to divide this by T, and then T's go away, right? So I'm just going to rewrite that. I have PV over T. And then that PV over T is equal to the number of moles times my constant. And my number of moles isn't changing. It's not even mentioned. So if it's not mentioned, it's not being changed. So this is equal to NR, and this is constant. So we're doing the same thing like we did a couple of videos ago with dilution problems. If I put some 1s here, and then if I do the same thing with some 2s, it's still equal to the exact same number because that's constant. So if P1V1 over T1 is equal to a number, and P2V2 over T2 is equal to the same number, then P1V1 over T1 is equal to P2V2 over T2. And that's going to be my equation. You probably learned this one as the combined gas law. Sometimes we're not varying that. Sometimes we're just varying the number of moles and pressure. And if we do that, I would do the same sort of thing. I would start with my ideal gas law. If we go back up to it here, get rid of all this other stuff. Start with my ideal gas law. Get everything that's varying on one side, everything that's constant on the other, and then set the two things that are varying equal to each other. That's going to be the formula that we're going to use. And we can do another type of problem after this one, so you can see that again. So now that I have that, we're just going to plug our numbers into it. So P1 is 760 millimeters of mercury. V1 is 4 liters. T1, 273 Kelvin. That's equal to P2, which is 782 millimeters of mercury, multiplied by V2, which is my unknown, over T2, 298 Kelvin. And then we just want to solve for V2, and that will be my answer. As far as units, these guys are going to cancel, my kelvins are going to cancel, and then I'm going to be left with liters as my final unit. This is why we need to make sure that they were both under pressure, that they were both either millimeters of mercury or both atmospheres, so they cancel. Again, the temperature needs to be in Kelvin. You don't have an option on that one. So I'm just typing this into my calculator now. And I get that my new volume is 4.24 liters. So my volume went up a little bit, not a ton, but it went up a little bit. Right? My temperature went up some, but not much, as did my pressure. So if the temperature went up some, right, they're moving faster, so your volume would have to increase. But my pressure also increased, so the number of collisions increased. So the pressure, the volume didn't go up as much as it would have had my pressure remained constant, if that makes sense. Just kind of relating what these things mean back to our gas laws. So we'll do one more where we kind of have to make our own equation based on the ideal gas law. So an example for us, if 3.42 moles of gas are in a container at a given temperature, its pressure is 1.73 atmospheres. We want to know what is the pressure if 1.00 moles of gas is added to the container at the same temperature. So again, kind of a lot going on, so I'm going to make that list again. This time the only thing that I'm varying are my number of moles, right? I have 3.25 moles and then an additional 1 mole, so I have 2 sets of moles. And then I have a pressure at the first amount of moles, and then we're solving for the pressure at the new one. So I know that N is 3.42 moles, and then P at that number is 1.73 atmospheres. So those are going to go together. We're adding 1 mole, so be careful. I'm not saying there's 1 mole in there. I'm saying we're adding 1 mole. So I'm going to have 3.42 plus 1. So I'm going to have 4.42 moles, right? 1 mole was added, so we now have 1 additional mole. And we want to know what is that pressure. So I'm going to do very similar to what we did in the last one. I'm going to take my ideal gas constant, PV equals nRT. The only thing that's being changed is pressure and my number of moles, right? The container's the same, so volume's the same, R is constant, and then my temperature is remaining the same. So I'm going to rearrange this equation so I get the things that are varying on one side. So I'm going to take and divide both sides by N, and then I'm also going to divide both sides by V. So I get this. And then this is constant. So we'll do the same thing. If my initial pressure times my initial volume is equal to that number, and then because it's constant, my new pressure divided by my new number of moles, sorry, I might have said that wrong, so pressure over moles are equal to a number. My new pressure and my new number of moles are equal to the same number, then those guys are equal to each other. So P1 over N1 is equal to P2 over N2, and then that's the formula I'm going to use. So again, we're just taking our ideal gas law, we're rearranging it so the stuff that's changing is on one side, the stuff that's not changing is on the other, and then we're setting the 2 things that are changing equal to each other. Once I do that, I can just plug my numbers into that equation. So P1, 1.73 atmospheres over 3.42 moles, that's N1. That's equal to my new pressure, P2, that's my unknown, over 4.42 moles. And then those moles will cancel, and we'll be left with the atmospheres for our units. So 1.73, I'm just grabbing my calculator here, divided by 3.42, multiplied by 4.42. And I get that my new pressure is 2.24 atmospheres. So another example for us. Let's say how many moles of methane gas, which is CH4, are in a container with a volume of 1.00 times 10 to the 5th liters, so a very large container at STP. So this one is actually just a straight ideal gas law equation. We don't have to do any rearranging and coming up with our own equation. We're looking for the number of moles, so N is going to be my unknown. I do have a volume given, 1.00 times 10 to the 5th liters. And then this is kind of what I was talking about earlier, how a lot of times it looks like we're missing information and we're not. Because we're told that it's at STP, we do know our temperature and pressure. It's just that if you didn't remember what those were, then you wouldn't be able to do the problem. So do know that at STP, my temperature is 273 Kelvin, and then my pressure is 1 atmosphere. So again, 1 atmosphere, 273 Kelvin, which is 0 Celsius. It just does have to be in Kelvin for all of our gas problems. Our gas constant then, again, getting it from the table, just make sure you use the right one for mole Kelvin. So we do have everything we need for this problem, and it's just a matter of plugging them in, making sure that our units are correct. The volume was given to us in liters, we don't need to convert that. We have Kelvin, we have atmospheres for temperature and pressure, so we should be good to just plug everything in. So my pressure, 1 atmosphere. My volume, 1.00 times 10 to the 5th liters. My number of moles is my unknown. My gas constant with its giant unit, and then my temperature. So my units are going to cancel, right? This liters with this liters, atmospheres with atmospheres, Kelvin with Kelvin. So we're going to be left with moles. It's actually, when we do the math, we're going to divide both sides by this part to get N by itself. So our units are actually 1 over moles, which turns out to be moles. So my calculator, plug this in and get an answer. Times 10 to the 5th. And I get a big number, but that makes sense to me because I have a very large container, right? 1 times 10 to the 5th liters is a big container. So it's going to hold a lot of gas. So from my calculator, I'll just write it down and then we'll get the right number of significant digits. I have 4,463.8. There's some additional digits after that. I want 3 sig figs in my answer, so 3. So the first digit I drop is a 3, so we can write this as 4,460 moles, which is 3 significant digits. Remember, we were using the rule where if you have a 0 at the end, right, a trailing 0, and there was no decimal point, it doesn't count as far as its significance. You could write it in scientific notation, which is actually probably a more accurate way to do it. Times 10 to the 3rd, right, we'd move the decimal place 3 moles. Either one of those is fine. They're the same number. So 4,460 moles.